Hello, everyone. Welcome to the Study in Study Abroad webinar series. Thank you for joining us today. We are pleased to host this session in collaboration with Lancaster University, a highly ranked UK university with a global reputation for excellence in research and teaching. Lancaster is a consistently ranked among the top 15 in all three major UK university league tables and continues to build a growing reputation with both nationally and internationally. We are honored to have Professor Graeme Burt with us. Professor Burt will provide a 20 minutes tester lecture on electronics and electrical engineering with Lancaster University. After the presentation, there will be a dedicated Q&A session where the professor will address your questions on studying at Lancaster. So please get ready to be inspired and let's dive into what makes Lancaster University an excellent choice for your academic journey. Without further delay, I'll now hand it over to you. Over to you, Professor.
Hi there. Thank you for joining us. My name is Professor Graeme Burt, and I am the Director of Studies for Electronic and Electrical Engineering at Lancaster University. I'm also a visiting member of staff at CERN as well, on top of that. I'm going to share with you today the first lecture that is part of my course on high frequency electronics, which we currently teach at Lancaster. Lancaster is world leading in high frequency electronics, both in our radio frequency, going all the way up to terahertz frequencies. As I've mentioned, I'm a visiting member of staff at CERN, where I develop radio frequency systems for the Large Hadron Collider. In our department, we also have a large group on next generation communication technologies, looking at 6G and beyond, looking to push up to the 100 gigahertz communication bands and even further. There's some at 200 gigahertz they're looking at, which would allow significantly higher data rates than current telecommunications. And we also have a large area in terahertz, which is becoming a technology really important in the future for scanning technologies. So when you bring all of those together, we have a wide area of experience at Lancaster. It's not our only expertise. We have huge expertise in robotics and renewable energy, and nuclear, and system on chip, microfluidics, nanoelectrostructures. But today's lecture focuses on the high frequency area, which is the group I lead. So high frequency electronics is to do with the band we are interested in. So we're particularly talking about, when we talk about high frequency, as the microwave band, including the millimeter wave, which is 300 megahertz to 300 gigahertz, and the terahertz band, which is 300 gigahertz to 3 terahertz. So we have a very large range we're talking about here of 300 megahertz to 3 terahertz. The question is, why do we differentiate this out? Why is high frequency electronics different from optics and from traditional AC electronics? And it's to do with some of the approximations we apply when we learn basic circuit theory no longer applies in the microwave band. And the same with optics. We make different approximations when dealing with optics that do not apply in the high frequency band. So it has to be treated separately than the other frequencies. So for microwaves, we're talking pretty much things on the millimeter to centimeter scale, going all the way to terahertz, which is in the sort of size of a human sand, the size of a human cell in terms of wavelength. So small scales, but quite a wide variety in there. So why is digital high frequency electronics important? Well, as I mentioned, it behaves slightly differently than what we do at lower frequencies. Let's take, for example, digital electronics. Digital electronics we like to think as being something that's different from analog, but in reality, all digital signals are analog signals. It's a square wave still has a frequency domain representation of itself, and things like dispersion and reflections can change the shape of a square pulse, a 1 and a 0, as it gets transmitted from one device to another. So we need to understand that to understand high frequency digital electronics. We need to understand the analog approach. Traditional electronic circuit theory is based on approximations and assumptions, most of which do not apply at high frequency. We assume all components are ideal and linear. So we assume if we have a device called a capacitor, it has capacitance but has no resistance or inductance, and its capacitance does not change with frequency. As we go to higher frequencies, that is no longer true. We also imagine that information travels instantaneously from point to point, which is good at low frequencies, but at high frequencies, the small delays going from instrument to instrument can be very important. And then when you do a circuit diagram, the length and the path of the wires tend not to matter at low frequencies, whereas at high frequencies, when you do a circuit diagram, you must state the length and shape of every wire, because changing its length or shape can change its capacitance or inductance. So at high frequencies, these become very important and need to be treated differently. So let's take an example. Let's say we've got a light switch connected to some power supply and a light bulb. Right? When we flick the switch, the light bulb turns on. But how long does it take for the light bulb to switch on? Let's say there's a meter between the switch and the light bulb. Well, what time scale will it take? What delay will there be between the light switching and the light going on? Now, if we ignore the heating up of the wire for a minute, just in terms of the voltage getting to it, roughly, electrical signals travel at roughly either the speed of light or somewhere around about half the speed of light, depending on the cable material, which is around 30 centimeters per nanosecond to 15 centimeters per nanosecond. So in a meter, it might take 6 or 7 nanoseconds to get from the source to the light. Now, at low frequencies, 6 nanoseconds is not a long time. But if you remember that the period of a 1 gigahertz signal is 1 nanosecond, it would be 6 periods of the RF signal before the signal got to the component. And that can be very important. Anything that becomes an appreciable fraction of a period can have unwanted effects in circuits. It can have phase shifts when we've got this constructive interference between two signals. If there's a small shift on the order of a nanosecond between them, you can cause them to destructively interfere or constructively interfere. And that becomes a major problem in electronics. But how do we represent this in circuit theory? There is nothing in basic circuit theory that handles delays on lines. So we need to change our mathematical approach in order to represent delays on lines effectively. Let's consider if a signal has a delay, then information must be flowing in a direction. It must go from one place to another. So signals don't change instantaneously, they travel from one place to another. We have a pulse, if you like, that is moving along our wire. The length of the transmission line affects the phase and timing, but also signals can be reflected. Right? If we have a pulse that's moving from one place to another, if it sees an impedance mismatch, the pulse could send some of its power backwards and some of it forwards, which will end up the signal splitting in two and causing echoes. If you've got a digital system, if you've got an echo, then that can really throw off your system. Frequency can also affect the behavior of components dramatically. The delay is a fraction of a period. If you change your frequency, it becomes a different fraction of that period. And therefore, it completely changes the way that circuit will behave. So how do we make this consistent with everything we know about circuit theory? It's very important we get it right. I give the example of the iPhone 4. I know it's quite old now, but it's a very good example because it was a very public failure of electronics. And the iPhone 4, they had a black strip to separate the antenna from the phone's body. But when you put your thumb over that black strip, the stray capacitance caused the antenna to be mismatched and sent all of the power back to the amplifier. None of the power got out of the phone and wasn't radiated. Essentially, you could not make phone calls if you held an iPhone 4 in your hand. Clearly, that's a big problem in a phone. And it was caused by a lack of understanding of high-frequency electronics, understanding how signals propagate and the effect a stray capacitance can have on an electronic circuit. So it's important we understand these things so that we don't get problems again. No one has made a similar mistake since in the phone industry because it was very embarrassing and all the iPhone 4s had to be recalled. But other things have happened in other industries due to lack of understanding of high-frequency electronics. So in order to model this mathematically, we must consider a wire, or in this case, a microstrip line on a PCB. We must consider it as a transmission line. What we mean by that is we have a distributed capacitance along the microstrip between the strip and its ground plane. And we also have a distributed inductance along its length. And that inductance and capacitance is what causes the delay in the line. Now, we can't really model discrete continuous elements as circuit components. So what we do is we break it down into infinitesimal segments. And in each segment, we give it one capacitor and one inductor. And we chain these together. Right? And the inductance for each value is given by the inductance per unit length of the strip line divided by the length of the cell. Now, you may have seen this circuit before. It's because this is a low-pass filter. Right? Now, wires are not low-pass filters. They propagate at high frequencies. But the inductance and capacitance, their values reduce as the circuit element gets smaller. And remember that we're modeling this as a distributed capacitance and inductance. So if our cell lengths get smaller and smaller and smaller, our approximation gets better and better and better, and the corner frequency of the low-pass filter gets pushed up and up further away from our band of interest. Roughly, the cell length should be about 10 times smaller than the wavelength in order to get the right behavior. But what it does give you is the voltage across each capacitor is shifted by a small phase. And the shift in phase is frequency dependent. So if we place a pulse here, there will be an oscillation around here with each capacitor filling in turn with a slight phase shift. And the signal will take an amount of time to get along this line by the filling of each capacitor, then the filling of each inductor, then the filling of each capacitor. And it causes a delay on the line. And this can be used to model exactly a wire's behavior at high frequencies. If we try to do it mathematically, if we neglect the losses, we're left with just the inductance and the capacitance. If we apply Kirchhoff's voltage law, which is the sum of voltages around a loop summed to zero, we get the voltage at port 1 minus the voltage drop across the inductor minus the voltage drop across port 2 equals 0. If we take Kirchhoff's current law, which is the current flowing into a node, is 0, then therefore the current coming into the capacitor node minus the current that flows through the capacitor minus the current that goes to port 2 equals 0. If we divide by delta z, both equations, and we take the limit of dz equals to 0, these reduce into two equations. The partial v over dz equals minus L partial I over dt. And the partial spatial differential with current equals minus the capacitance times the partial differential with time with respect to the voltage. So this is known as the telegrapher's equations that give us the relationship between the voltage variation in space and the current variation in time, and vice versa in that circuit. But it doesn't give us delay yet. To get delay, we must combine them together. If we take dv over dz equals minus L over di over dt, and we differentiate with respect to z on both sides, we get d squared v over dz squared equals minus L times d squared I over dz dt. But we remember from our previous equation, we also had the equation for di over dz, which we can insert into this equation, and we get the change in voltage, the second order differential with respect to space of the voltage equals the current times the capacitance times the inductance times the second differential of the voltage with respect to time. That tells us that the variation in space for the voltage is proportional to the variation in time. There's a solution to this equation, and the solution is given here. The voltage is given by two components, a forwards voltage and a reverse voltage. And you can see the exponential in here, z over square root LC minus t, and z over square root LC plus t. If the peak occurs when the exponent equals 0, then in the left-hand equation, as t increases, as time goes forward, z must go forward to keep it at 0. So that tells us the wave must travel in the positive z direction. The other term has z over square root LC plus t. So as time goes forward, as t increases, z must be negative to keep the exponent at 0. Therefore, that wave travels in the minus z direction. So this gives us the representation of an instantaneous voltage as two waves, one traveling forwards and one traveling backwards. And by combining these together, we can model any circuit behavior. It gives us that propagation. It gives us the velocity as well, because the velocity is proportional to the square root of LC. So we can see here that we now get the behavior of a wire at high frequencies by applying these very simple equations. Now, we get a problem at the interfaces because the instantaneous voltage and current cannot change across an interface. Right? But we know that the traveling components can vary. So by combining different traveling wave components, we can sum them together to keep the voltage and current continuous at the boundary, while also respecting the impedance in each section. So if the impedance on one side is different than impedance the other, impedance is V over I, therefore the ratio of V over I must change for the forward wave component and the reverse wave component, but the continuous voltage, instantaneous voltage at the boundary must remain the same on both sides. So we get that by summing them together. We know that the instantaneous voltage is the sum of the forwards and reverse voltages. And we can derive a similar equation for the current that tells the instantaneous current is the forward current minus the reverse current. So you can see here, if we get a large reflected signal, the instantaneous voltage goes up and the instantaneous current goes down. Therefore, our impedance increases as we have in a reflection. So if our impedance is bigger on one side of the interface, if we create a reflection, we can change the voltage to have a higher impedance instantaneously, but while keeping the right impedance for the wave components. We can derive what strength the reflection must have to maintain these conditions. If we imagine we have two ports, we have port 2 and port 1. The voltage at port 2 equals the sum of the forward and reverse voltages at port 1. Now we know this because the instantaneous voltage must be the same on both sides. Now on the second side there is no backwards component because there's nothing to reflect off of. You only reflects at the interface. So the instantaneous voltage on the second side is just the forwards voltage. On the first side, where we have a reflection, we have the forward and reverse voltage superimposing. And we can do the same with the current, apart from on the first side, it's current, the forwards current minus the reverse current. The impedance, which must be the same, is V. The impedance in port 2 is the voltage at port 2 divided by the current in port 2. So that's given by the impedance of the line. And we know that that must equal the sum superposition of the voltages and currents on the other side, because the voltage and current must be continuous. So therefore, Z2 can also be given as the forwards and reverse voltages summed divided by the forward and reverse current subtracted in port 1. We can then introduce something known as a reflection coefficient. The reflection coefficient is the ratio of the forwards to the reverse voltage and the forwards to the reverse current, and it's the same constant for both. If we then insert the reflection coefficient into the equation above for Z2, we get Z2 equals the forwards voltage in port 1 times 1 plus torr, which is the reflection coefficient, over the forwards current times 1 minus torr. We can rearrange this because we know that the forwards voltage in port 1 over the reverse voltage in port 1 is the impedance of port 1. So we get Z2 equals Z1 times 1 plus the reflection coefficient over 1 minus the reflection coefficient. So we can rearrange this to tell us the proportion of the forward signal which is reflected is the subtraction of the port 2's impedance minus port 1's impedance divided by the sum of the two impedances. And this will allow us to keep the voltage and current continuous instantaneously while also maintaining the voltage and the impedance on both sides of the interface. Now, a reflected signal is not something that happens in AC electronics. It's a distinct thing that happens in high-frequency electronics. The reason for that is all the reflections cancel out at low frequencies, whereas at high frequencies, because of the delay, that doesn't happen. So the addition of forwards and backwards waves allows the time and phase delays to be included in existing circuit theory. You know, everything we used to derive this was Kirchhoff's laws, voltage and current. So just by applying Kirchhoff's voltage and current laws and representing a wire as its realistic capacitance and inductance, we're able to include the time and phase delays. Ohm's law is obeyed for both traveling and instantaneous voltage and currents simultaneously. And the instantaneous voltage and currents are continuous at interfaces with the addition of reflections at that interface. The amount of reflection is related to the change of the impedance of that interface. And that's very important because in the iPhone 4, the additional capacitance caused an impedance mismatch, which caused all the signal to be reflected. And if we can understand the reflection, we can understand how these will behave at high frequencies. It's very important that if you're trying to get power from one device to another via an antenna or via wires, we want all the power to get to its destination. If the power is reflected, the signal going forward is reduced, and that can cause us to fall below logic voltage thresholds and can cause ones to become zeros. It can cause weak signals and reduce range in communications devices. So it's very important. Okay, that's I'm going to finish there. It was just a taster in sort of what we do as the first lecture on the high frequency course. The course goes on to go into more depth where we design amplifiers, antennas, filters, all at high frequencies. We then build those components in PCBs, and then we measure them using network analyzers. Now, our department has been lucky enough to have a large number of network analyzers, so we're able to have each student have one per student at the desk, which is quite rare. We've invested quite heavily making sure that we have all the equipment to do that. We've also got some small RF diagnostic chambers to avoid any outside noise affecting our measurements, and we're in the process of building an anechoic chamber for antenna measurements as well. If you are interested in high frequency circuits and electronics, you would also have the opportunity to do a final dissertation project on high frequency electronics, and we have many areas of that. For example, I have had a large number of students do projects with CERN, and even I've had about 5 or 6 students actually go to CERN to visit to do measurements. Claudio, who's the head of our terahertz group, has worked with a lot of major mobile phone providers and can do projects on that. And he has a state-of-the-art 1 terahertz network analyzer, plus fabrication facilities to make terahertz components. He's got a brazing station and an electroplating station, and all the high voltage stuff required to get it to operate. We also have expertise on using DSPs to control high frequency electronics as well as many other areas we work on. We've got industrial processing using microwaves, and we've also worked with the European Space Agency looking at satellite communications, and on fusion looking at terahertz sources for diagnosing the plasma's behavior. So we have quite a lot of hardware. We have the ability to do projects with some very big employers and some very interesting national laboratories and international laboratories. So you would have an opportunity to do projects that you wouldn't get at other universities through our networks. Another big selling point of Lancaster is the industrial project. We're the general engineering department, which means we do mechanical, we do electronics, we do electrical, we do nuclear, we do chemistry. We get the students to work together to do a work for a company. We get industry to come in, set a problem for the students, and then they have 3 weeks to work on that problem with an industrial mentor. So you have a chance to get involved with industry both through the dissertation, but also through this industrially linked project. We are very much a design, build, test department, so we believe very much on students getting hands-on experience with hardware, particularly in the MSc. Almost all our courses have a large practical element associated with them, using some state-of-the-art equipment. But I think that's everything I had. I think I'm going to hand you over now to Johnny, is that right?
Yeah, that's right, Graham. Thank you so much for that overview of one of the taster sessions. That was fantastic. So I've got some slides about Lancaster and very briefly about the engineering school, and then we will have time for questions at the end. So I'm going to get through this as quick as I can to allow time for that. I've seen some questions coming through on the live feed too. That's great. What I'll do as well is I'll ask Tanil, Aditya and Alua to switch their cameras on just to give us a quick wave as well. So say hello. Tanil, Alua and Aditya are current students at Lancaster. They're based within a different part of the university within computing, but they can absolutely help with any questions about the student experience and what it's like to come to the university as an international student as well. So yeah, I'd like to share with you all some information about where we're speaking to you from today. You can see from Graham's background that he stood outside the engineering building, technically. But this is a picture of our campus. So for those of you who've not experienced Lancaster before, we're located in a beautiful part of the northwest of England. Everything that you can see here in front of you is our university campus, with all of our accommodation facilities, places to go to grab something to eat, meet up with friends. Everything is really within one location. And I'm sure you'll agree it's a very beautiful part of the world too. In terms of where we are in the UK, so we're in the northwest of the UK, as I mentioned, and we're really well connected to other parts of the country. So I'll just go back. So you can see our campus then in the foreground, and then in the background or on the left, you can see the city of Lancaster. So we're located very, very close to the city of Lancaster itself. And then not far away from these cities you can see, such as London, Manchester, Edinburgh, Birmingham, and even further afield. We have excellent rail connections, so you can travel to Manchester Airport just over an hour. So, if you're coming from India, from other parts of the world, you can get a flight to Manchester Airport, and then from Manchester Airport, you can be on the train, and there's a direct train to Lancaster. So it's really, really easy to get to us. And it's important to remember that, the scale of the UK as a place to study, it's very, very different to India. We're a much smaller country, so you can get around very easily, and it doesn't take, any time at all. As Rahul mentioned right at the beginning, Lancaster University has an excellent reputation, both within the UK, in UK league tables, but also internationally as well. This is in areas of our teaching, employability and careers, but also, in the research that we offer. We're a collegiate university at Lancaster as well, which is quite a unique experience. So all of our students belong to a college, which work a little bit like houses, and we have a dedicated postgraduate college as well. So for our students coming to us to do masters and PhDs, they will all live within graduate college or be a member of graduate college. You can live on campus as well. We have dedicated facilities there, but there's also a range of accommodation choices in the city of Lancaster. But your college at Lancaster is very much your home. And Lancaster as a place is very much a hidden gem in the United Kingdom, and I've been here for a good while now, about 10 years when I think about it. First as a student and now as a member of staff, and it is a really, really historic city. It's a very international city as well. We have students from all around the world, and it's a very friendly place to be. And there's lots going on across the year, from food festivals to music festivals. And actually, I will say some really good restaurants and some great places to grab a tea or a coffee. So I don't want to go through this in too much detail, as Graeme has covered some of these areas already, but really it's just to say that, our School of Engineering at Lancaster has an excellent reputation in the UK and also worldwide. It is a medium-sized department with approximately 650 undergraduate students and 180 postgraduate students. And we have academics and students from all over the world. And it's a very friendly atmosphere, very friendly department. And we're not just saying that because we feel like we have to, we generally mean it. And you'll have access to some amazing facilities, some amazing pieces of equipment, which Graeme has already highlighted. And we also have our brand new engineering building as well, with access to the facilities you can see there on the screen. Within the School of Engineering, we have teaching undergraduate and postgraduate level, and this is really just to highlight the breadth of teaching that we have. Again, not to go into detail here too much, but also to highlight that we work with a variety of external companies and partners which feed into the curriculum that we have at Lancaster across undergraduate and postgraduate teaching. We have a range of MScs. This session is very specifically for those interested in electronic and electrical engineering, but really just to say that we do offer teaching across a few different areas, such as advanced mechanical, engineering project management, and also electronic engineering as well. And students go from Lancaster into a variety of different careers, and we support them very closely with a dedicated careers team. Our careers team are both at a university level, but also we can offer departmental or specific advice related to the engineering sector. And students graduate from us and go into a variety of different roles, some of which you can see listed there. for our MSc Electronic and Electrical Engineering, I've got some information here about the course. I'm not going to go into lots of information. Again, I think Graeme has covered this quite well. But actually, Graeme, can you ask you to give us a bit of an idea of the kind of students that you're looking to come onto the course? I've got entry requirements there. But in terms of the students that you're looking for, what are the main prerequisites that you'd be looking for electronic and electrical engineering?
Well, there's a lot broader than our electronic one. Our electronic one, we have specific needs. We would like students to have some sort of experience of digital, because there's a lot of digital in the course, and sometimes electrical degrees can be light on digital, and that can sometimes be a problem. So that's something we would definitely want from most students, and some amount of electromagnetism, but most electronic and electrical students have that. But other than that, I think that's it for prerequisites. I think we teach everything else. The electrical side, you know, I think it's a course that can be picked up with you, whether you have that experience or not, if you only have an electronics background. And I think the high frequency electronics just need electromagnetism. And the digital stuff just needs some amount of background of probably just microcontrollers is probably fine, but we will use more advanced stuff in the course. But if you've at least done microcontrollers, that should be fine.
That's great. Thank you, Graeme. So just before we go to the Q&A, really just to highlight that we have scholarship provision for students looking to do master's courses in engineering, but also across the sciences at Lancaster. So we are offering a number of awards. All of the information about the scholarships are available on the Lancaster University website. This is for students looking to join us this year in October. We have the Lancaster University Global Scholarship, but also the Faculty of Science and Technology Dean's Awards. In shorter terms, if the students who achieve a equivalent of a first class honours UK degree, they are eligible to receive a £10,000 fee reduction scholarship. And for those who achieve a 2-1, they are eligible to receive a £5,000 tuition fee scholarship. If you have questions about the scholarships or any of the course information here, I'd really encourage you to book an appointment with one of the counsellors at Study In, and I'm sure they'll be more than happy to talk you through the specifics of how to apply scholarships as well at Lancaster. Okay, so now we have time for the questions. I know we've had some come through. At this point, I'll hand over to Rahul to run through those that have come through in the Q&A. So over to you, Rahul.
Thank you everyone for the insightful presentation. Now, time for the Q&A session. I'll read out the questions from the YouTube chat box. So the first question is, what kind of hands-on experience can I expect during the electronics and electrical engineering courses?
Well, we have a large number of hands-on experience courses. I mean, for everyone slightly different because of the dissertation. So a large chunk of your hands-on experience will come in the dissertation, which you would have the choice of projects across a wide variety of electronic and electrical. But in the modules themselves, I mean, I can say in my course, as I say, every student builds a higher order Butterworth filter, and they measure it and they design it and microwave. We do a lot of simulation type stuff in that, and then we build the PCB and then we measure it at the end. So that's something that comes in mind. With the digital course that we do, we have this robot that balances a ball, and you've got to use a control system that moves it forwards and backwards to get the ball to stay stable. So it's a bit programming hardware. We use the ARM chip for that, for example. There's a control class where people are, there's a heater they're trying to control with the intelligent control systems module, where that's about control. There's a computational lab using ComSol for the microengineering course. That's not hardware per se, but it's simulation based. I think that's most of the practicals we have as part of the course. But the big thing is the dissertation. So you could pick a project. If you want to be more practical, you could pick a practical project. If you want to be more simulation, you pick a more simulation project. It's very flexible. The way it works at Lancaster is we don't assign you a project, we assign you a supervisor. So that each mentor or supervisor provides their expertise in a list, and you pick a mentor, and then that mentor and you will define the project together. So it gives the student far more control of what the project is. Many other universities, there's just a list of projects and you just got to pick one. Here, the mentor will help you devise the project. We want you to be in control. So if you want a practical project, then that can happen. You have the control. So you decide. Often students don't know what they want to do. So what can happen is you'll meet with the supervisor and you'll say, well, I'm really interested in doing something practical in this sort of rough area. And they would suggest to you potential projects you might want to do. Or sometimes students know exactly what they want to do, and they come in and say, I really want to do something on edge computing, and I want to do this particular project, and it happens. So that flexibility that we give our students to really be in control of their own dissertation project gives you a lot more flexibility to put in whatever you want. So if you know you want to work in the telecommunications industry, you can pick a project with one of our telecommunications supervisors, and you can say, well, I really want to do 6G measurements in the lab. I want to build a 6G amplifier and measure it in the lab, and that can happen. Or you might want to do something that's more control based, and we have lots of robots. You could be building a robot, but also you could be controlling one of our existing industrial robots. So there's a huge variety of things you can do because the way we assign those projects, giving the student the power. But in terms of what labs we have that you could make use of in the projects, as I say, we've got state-of-the-art network analyzers for high-frequency measurements. We're building an anechoic chamber. We've got terahertz spectroscopy set up. We have a microscope lab for looking at thin films and circuit components on a very small scale. We have microfluidics capabilities. We've got a lot of renewable research. We are quite big on wind turbines and wave power, but we're also got quite a bit on batteries. And we've got a company that's spun out that we work closely with that builds batteries, and you could do a project with them if you were really interested in it. We do electric vehicles. We've got an electric vehicle project we run every year with the undergraduates, and we've got some experts in electric vehicle design and powertrains. We've got I think that's most of the core strengths we have in the department in terms of facilities wise. I'm trying to think what we have in the electronic side, but I think that's mostly it. Obviously we've got lots and lots of robots and control systems and microcontrollers, FPGAs, DSPs. So there's a huge variety of things you can do.
Oh, great. Thank you. So the second question is, can I work on my own tech projects during the course?
Yes, of course. There's two ways you can do that. Number one, if you can have that project being your dissertation. Now, you'll need a supervisor to help you make that project academic enough to be graded, but you could do that. But also you have access to facilities during the course. I mean, you haven't got access to all the labs because there's safety concerns. If you wanted to rock up and use our 1 terahertz network analyzer, well, that's £1 million bit of kit. We wouldn't let students use that unsupervised on personal projects. But if it was your dissertation project, you could. But you can certainly use we've got 3D printers, soldering stations, DSP type stuff. You can get access to all of that for personal projects. But the The things that are very expensive or have safety issues, some of the high voltage stuff, we wouldn't allow students to use independently unless it was part of the dissertation.
Okay. So the next question is, what support is available for finding internship or placements?
Well, we have a member of staff who's now starting to help find placements and internships for the undergraduates. We don't really do that very much with the postgraduate because it's a one-year course, so that you haven't really got that gap year to do something in between because it's an intensive 12 months. So we don't have now we've got the career service, we can help you find a job afterwards. That can help you. And our staff have a lot of contacts. So our staff can help you find posts as well. We do have staff that do help our undergraduates find placements, and I'm sure they would help postgraduate, but there's no gap in the schedule for you to do a placement. Certainly, doing dissertations with industry is possible as well. We can help you. A lot of the supervisors have industrial contacts, and it's possible to do dissertations with industry. There's the Industry Link project, which is automatically with industry. So that's like a mini internship. It's a 3-week internship, if you like. It's an Industrial Link project. So that's set and guided by industry. So that's an automatic. But there isn't really, as an undergraduate, you have gaps in between years, and we help our students get placements then. The MSc is not quite set up for that because we don't have that gap.
Okay. So I have covered all the questions from the YouTube chat box. Thank you for answering all the questions so well. Would you like to share any final words?
Thank you, Rahul, and thank you, Graeme, for those answers as well. But quickly before we finish, I'm aware that we've got a couple of our current students here, and I have a couple of questions for the students. Is it okay if I ask them now, Rahul?
Yeah, please go ahead.
Fantastic. So the first question I've got is actually I'm going to go for Tanil. I've picked on you first, Tanil, because I can see you on the screen. So my question for you is actually, how would you describe our campus at Lancaster for those people who've not been to us before, they've not experienced it? You know, maybe you can tell us about your first experience of it and, you know, how that kind of like made you feel. So yeah, what's your thoughts on that?
Sure. So my experience of the campus has been fantastic. Like mentioned earlier, everything is split up in colleges. So, for example, as a postgrad, you'll be in the graduate college, which is really great because that means you live with people going through the same phase of their studies. You stay together, you do socials together, which makes it very easy to kind of familiarize yourself with everyone that you'll be studying with and like-minded people. And in terms of getting involved with the university, I think we have over like 200 clubs and societies. So there will be something for you to get into, whether it's on the sports side, whether it's more academic based. There's something for everyone. So I think the university offers a lot of support as well. I know someone asked about career support. We do have like your career expos where you could meet people, network, things like that, and use our career service where basically, you know, anyone can go up to them to ask for advice on their CV or what they should be doing for the next step. So all around, it's a great university, and, you know, there's always someone you can go to for anything you need. So it's been a great experience.
That's great. Thank you, Tanil. Aditya, the next question I've got is about the college experience at Lancaster, specifically graduate college. Could you tell people a little bit more about graduate college? And actually, but you live in the city of Lancaster yourself, don't you, Aditya? So maybe you could tell people about what it's like to live in the city, still be a part of graduate college, and how you can access the different events that happen.
Yeah, sure. Thank you. The city of Lancaster, it's small, but you know it's quite great. You have a lot of places to go for a walk, and you can get everything for shopping, all type of South Indian groceries, Indian groceries, and you know every other things which you wanna take. Also, I mean, I suggest people to live on campus because you know there are a lot of events going on every day. You just open our Instagram page and you will find a couple of events going on daily basis. I mean, I go to university and I attend as much as I can, but at the end of the day, you miss some things. But yeah, living at city gives you flexibility as well. You are better in terms of transportation. You live near railway station, bus station, and all those things, which make it easier. If you love traveling, it becomes easier. Yeah, but I would suggest, I would highly recommend to live on campus. At the end of the term, you miss some things.
But I guess just to say, it's quite easy to get from the city to campus as well.
Yeah, it's
How
like
often?
a 15-minute bus travel. If you take bus, it's like 15 to 20 minutes. So it's pretty easy, and you have buses at like 5 minutes interval in the morning, and during daytime it's a bit longer. But yeah, it's pretty convenient. And some people just like it's a sunny day in UK, so sometimes we just go walk to the university, or walk back to the city center, and it's lovely. You have all the greenery patches in the route. It's lovely.
That's it. Thank you, Aditya. Alua, so last question for you. So, where's your favourite place to go in Lancaster? If the weather is as beautiful as it has been, recently, where do you like to go? What do you like to do?
Since hi everyone. Okay, since I'm living in a campus, it's sometimes worse to go out and especially go to the city center because sometimes you get a bit bored. But most of the places that I would really recommend you to go is the cafe. That's called. Okay, I don't really remember the name, but this is the local cafe. Maybe guys will help me to remind that name, but actually, the cafe is so good because it's quite expensive than those that in the city center and the campus. But this place reminds me that my hometown sometimes, and if I go there, I just can able to sit in the work for a whole day. And the cafe is the quality of the coffee is so good. Also, I will recommend you to go to the just local parks, whatever you want, which was the closest. If you want to go for the campus, that is also good. So all the parks are so natural. You have all the time to go there. You see a lot of people are walking around, spending their free time, and a lot of people doing the picnic these days. So it's so good to spend time with the people that you really go with, and just spend the time and walk around. This makes me help. Sometimes it's reveal the stress as well because we have a lot of studies as well to do. So just attending the parks and the cafes is the best place to go, I guess. But there's no specific one for me.
I think it's really hard to choose which coffee shop's the best one in Lancaster. There are too many. Fantastic. Actually, Graeme, I'm going to ask you the same question. Where do you like to go in Lancaster if you have some spare time? Where's the one place you like to go?
Oh, well, for me, I live next to the large park, Williamson Park, where there's always something going on there. In the summer, they have plays in the park. There's a stage in there, an open air stage where they do plays in the park. We have a large music festival there every year. Where actually I get a free concert because it's my back garden, so I get a free concert every year with some pretty big name people that come along. Usually a couple of older bands, like we had Grandmaster Flash the other year there. But it's really good to have that music concert in that park, and it's got woodland walks for my dog. So I really love that. We're right next to the Lake District as well. So if you love the countryside, it's absolutely a beautiful place to live, Lancaster. I think yeah.
Sorry, just to start you. Yeah, when you told me about the Lake District, it just came to mind. Especially the best thing to do in Lancaster is to visit the Lake District, whatever is, which side it is, it's the best you ever have, I guess. So I guess it's the best place to go as well. Sorry.
No, not at all, Lua. No, it's an amazing place, and yeah, if I look out of where I'm in Lancaster now, I can see the hills in the background, and it does make me, want to get on the train and just go up there for the day. Thank you so much, Tennille, Lua, Aditya, and Graeme for sharing your experiences there. As much as I don't want to close the session, I think I'm going to have to hand it over to Rahul at this point. to finish the event for today. But to everyone who's been watching, thank you so much for joining us. As I mentioned before, if you have questions about our Masters in Electronic and Electrical Engineering, please book an appointment with one of the counsellors at Study In. I'm sure they'll be happy to help you with your application. And obviously, we would look forward to seeing you at Lancaster later this year. So at this point, I'll now hand over to Rahul to close the session for today.
Thank you everyone for your valuable time. All the audience, if you have any further questions, please feel free to contact the Study In office in India. For more updates, do follow us on our social media handles. Bye-bye. Take care. Okay.